final stage of the machine learning model lifecycle is now putting the model actually in production. So this now assumes that we've already explored our data, we've done all the pre-processing that we wanted to undertake, we've selected an algorithm that meets our needs and potentially intervened in the training itself, and we may or may not have used any post-processing techniques to change some of the outcomes. So the model's ready now to be deployed. So we're going to be in the final top section here of our lifecycle chart, where it's all about deployment. And in fact, one of the important things that we need to consider when it comes to deploying models is that the world around us keeps changing. So just because we've deployed a model once, that does not guarantee that the performance will be upheld in the future as well. So this is what leads us to retraining of the model. I already mentioned that we cannot assume simply that the world around us stays as was when we collected training data, and this is what we call the environment and or distribution shift of our data and features, and also labels actually. So a couple of challenges that we have to overcome here when it comes to deploying a model. So first of all, there are going to be different types of shift in our data, depending on whether it's the features that are affected or the labels. Bottom line though is that we cannot expect reality to exactly match the training process, especially if we talk about different use of the model in different points in time or in different geographic regions. So there's always this data shift that we can encounter from the model build stage to the actual deployment and use of the model in a production setting. One of the types of shift that I want to talk about now is the so-called covariate shift, whereby the distribution of the training features is different than the distribution of the test or production features. And as I just mentioned, that could have many reasons. The most common ones would be a temporal or a spatial shift. So basically time moved on, or we're looking at different geographic regions and different populations. And just to illustrate this with an example here, let's say you built a model that is making clothing recommendations, and you built your model in summertime, and all the training data that you used was with respect to clothing that was popular in summertime. And now, by the time you've deployed your model, it's winter, but you keep making recommendations based on the summertime features. So obviously now the test features have a very different distribution. Second thing that can shift is the label. So covariate shift corresponds to the feature shift, and the label shift now is the change in the distribution of the label between training and production or test setting. And one example here could be that you've trained a classifier, let's say, on an artificially balanced data set. Because again, here we already know that one of the problems in machine learning can be that models tend to perform better for classes that are more represented in our data set. So ideally we would sample so that we have the same number of data points in every class. But then when it comes to actually getting those images in a real world setting, the distribution might not follow that equal distribution that we used in training. So here the example is the image classifier, where we have balanced training examples, and then we could actually encounter non-uniform occurrences of different objects in the real world. The final type of shift I want to talk about is the so-called concept shift, where the definition of the labels actually changes over time. So that could be due to updated beliefs, maybe a revision underwent. And one example here is the medical diagnosis, where originally it could be a certain set of criteria that make up a certain disease, and then new findings come to light and the criteria change. So how can we actually go about correcting this shift? Well, first of all, it's going to be difficult to monitor manually, so we need something that's automated, and ideally also something that triggers an alarm, because we're not likely going to look at every single model that we build every single day or every month even. So what we want to do is we want to implement an automatic detection of the shift and then also trigger an alarm. So if we detect a shift, we would generally want to retrain the model, and SageMaker does actually offer model monitoring jobs for us, and we can also use those to trigger alarms. Obviously, we need to do all of that with respect to a certain baseline. So that is going to be the baseline that you get from training the model, and then we can measure deviations from that. How can we go about automated model monitoring in practice? Well, the first component that we want to monitor and check for drifts is going to be the data that was used to train the model, and that data that comes in to make and generate predictions. So we can run data tests, skew tests, and also perform data monitoring. The second component that we want to monitor is going to be the model itself. So that is on one side the code that makes up the model, and then also the model training process itself. So we can actually run certain tests to make sure that the model is in fact training as expected. And once we have a trained model, well, then the model is generating predictions, and we can actually monitor those predictions. We can check what are the output ranges or the output values, what are the min values, what are the max values, and compare those to the predictions that we're generating in a production setting as well. So we have a whole lot of tests here, unit tests, integration tests, and we can also perform system monitoring. So it might be that suddenly we see a spike in CPU usage, and that could indicate that something is indeed going wrong. The full picture now then is going to be here, where we have the data in combination with the code and then the running system as a whole. Let's start by talking about the data drift. What can we check here when it comes to our input data, and how can we compare that to the data that's coming in for predictions? Well, every feature that we have in our data set will follow a certain distribution. So we will have a mean, a center of the distribution, and then a spread around that mean or the center as well. And the idea is now, and this is what you see in the chart on the right hand side, that we might be training the model with features that follow a certain distribution, such as the one shown in blue. And here you have on the x-axis, let's say, the height in centimeters of individuals. And then suddenly when it comes to production and we're trying to generate predictions, well, then height is still going to be an input feature, so we can actually record that information. And if we collect a sufficiently large number of inputs that are coming in for prediction purposes, well, then we can regenerate the distribution as well. And what we can do next is we can actually compare the measure of centrality and the spread of these distributions between training and the production setting. So first we need to establish a baseline, which would be the blue curve in our example here, if that's what we used for training. And then we can compare the baseline to what we observe in the production setting. And once again, there are many different measures or ways to actually quantify how different the distributions are. One example that we're showing here is the Kullback-Leibler divergence, and you have the equation on the slide. More interestingly, we actually have Amazon Model Monitor as well. So this is a service, an API that can actually be used to monitor these different aspects. So as long as we set up a baseline, we can then compare the different distributions to that baseline. How would we do that in practice? So first of all, we need to record what are the characteristics and distribution in the baseline. And then we can set up certain configurations. And you can see here, we actually can do the same for bias configurations. So that would be calling out particular features that are relevant because they are either sensitive attributes or relevant to our bias analysis. So here we're showing the configuration, at the top the data configuration, and at the bottom the code for bias configuration, where we need to specify first of all what the good labels are, what the facet values are, and then also thresholds in case of this being a classifier. And next we can set up a monitoring schedule with the baseline, and this can now be done with or without the bias configuration. So here we're showing the configuration or the settings including the bias configuration. First couple of lines of code is the authentication, and then we have the configuration of the model results themselves, so the prediction configuration. And then we get the baseline calculation at the bottom where we provide all of the different inputs. So basically we're telling Model Monitor, what did the model look like? What does the data look like? What are the bias sensitive attributes that we want to consider? And also, do we have any particular thresholds or configuration for how we're generating predictions? Next, let's talk about model drift. So the idea here is that for different reasons, this could be because time went on, or we have a different geographic region that we want to use the model for, the model performance is starting to look different. And there are two scenarios of how the model results or the outputs could look different. On the left-hand side, we have a rapid drop, so a steep drop in the max predicted probability. So on the y-axis now, you have the predicted probability scores ranging from 0 to 1. And we see that from January all the way through December, the max predicted probability was hovering around 0.75. And then suddenly the predicted probability values, the max predicted probability scores, dropped down to 0.1. So clearly something went wrong. This could be because a data feature was left out, or maybe the scales were changed, or some other input has become erroneous. The right-hand side shows a much more subtle change where we have a slow drop in performance. So this is going to be a drift over time. And once again, the idea though remains the same, where we train a model, establish a baseline, and then we keep continuously checking if the model performance is still meeting the bar that we set in the baseline. So in the scenario on the right-hand side, we can see that we're first overperforming, but then as time goes on, eventually we drop below the performance threshold that is good, and then we can actually trigger a retraining of the model. Retraining, by the way, that might constitute collecting new data. It might be that at that point we need a completely different model. So that will very much depend on how different the performance is and what exactly the root cause is for the performance drop itself. So some examples of what could have happened, well, it could be that the feature engineering, the ingestion of the features has changed, and maybe the model was not adapted. It could be that the input features changed in units or maybe became unavailable. And if the model is heavily relying on a feature that then suddenly becomes unavailable, because maybe it's no longer being recorded, well, then we see a steep drop in the performance. It could also be that the model was updated with new data, but maybe the hyperparameters of the model were not tuned sufficiently. So once again, there are many subtle reasons and root causes of what could have happened. So this is going to be a bit of an exploratory task. In terms of how to set up model monitoring, we have another code example here where we can see that we're setting up a monitoring job, or rather we're creating the instance that will perform the monitoring. We authenticate, we provide the information of how many instances we want to use, the volume size of the instance type, and then also we limit the runtime with max runtime in seconds. The final check that we want to perform is the system monitoring itself. And here we have several different metrics that we can monitor. We could look at the memory and disk utilization. We can look at latency when calling the model endpoint, so how long does it take for the model to actually produce a prediction. We can look at system reliability or robustness, and in fact most of these metrics, most of these system performance metrics, we can actually look at those in CloudWatch. This now concludes our topic on bias mitigation in the machine learning model lifecycle, because we're now at the point where we're generating predictions or answers to the customers. We're not quite done yet, because one of the common things that will happen is once you expose a prediction to a customer or to a stakeholder or to a recipient of the output, well, then they will have questions as to why they received a certain outcome. And this brings us to the next topic of explainability.